You'll also notice, if you haven't already, if I come in here and I apply a new time, let's say 10:30 p.m., the moment I click apply, all of these are going to change. Hey guys, and welcome to Gem City Rail. So I want to talk first a little bit about what is the purpose of this video. I've created a synthetic time ecosystem that is useful to my use case, which is model railroad, but I think it has much broader potential. So I wanted to put this video out as sort of a feeler to see if there's any interest in this. Because really this is a tool I've created for myself, but if there's a lot of interest in it, maybe I'll share it on GitHub or something like that. So that's really what I want to accomplish with this video. So here's what we're going to cover. First, we're going to cover how I got here. I'm going to give you kind of a brief overview on the system I've created. Then we're going to go through some of my design goals when creating the system. Then I'm going to do a demo for you guys. Then I'm going to cover what I think are potential use cases. And then finally, we're going to cover what use cases I really don't think this is applicable to. So let's start with my goal. I've been thinking about a model railroad layout for about a decade now, and every once in a while I get kind of interested in it and I pursue it, and I've been making progress over the years. And my layout design is highly themed, and it requires ambient audio triggers, ArtNet lighting control, pretty sophisticated automation, sophisticated sensors, and I want everything controlled from a single pane of glass. That's pretty important to me. So I'm not a big fan of JMRI. I'm sure those people are lovely that have developed it. It feels antiquated to me, and I'm a software engineer, so I like to come up with my own things. So I want the unify network experience for model railroad is kind of what I'm aiming at here. I want all communications happening over the network. So everything must be IP based: time, control, automation, sensors, lighting. And the reason is because I want it all controlled from a single pane of glass. And if I'm going to accomplish that, I kind of need all the information on the network. So the first problem that I ran into when I started thinking about this was everything needs to be synchronized. In my layout, everything is very time sensitive in my theme of my layout. So I need a synthetic master clock system. Now we're not talking about fast time systems as they exist today. What I'm looking for needs to be modern, efficient, reliable, very importantly inexpensive, because model railroading gear can add up quite quickly, and it needs to be distributed. So I'm not looking for a monolithic type thing here. What I want doesn't exist, at least that I can find. So I built it. And what I've built is a system called Chronost. It's a synthetic time ecosystem consisting of a host application, a lightweight protocol, and low-cost hardware. This is the very, very simplified version of the architecture. So you have a host application that runs on some machine. I've written it in Go, so it is cross-compilable. I'm currently running it on a Raspberry Pi, which works perfectly adequately. But it can run on a Linux VM if you're on Proxmox or whatever. You could compile it for Windows. You could compile it for Mac. It'll run anywhere, basically. And that is the host application, and then you have clients. And the most basic example of a client is just a clock display. And I've built 4 prototypes that I'm going to demonstrate for you later in this video. But then, of course, the host application that I've designed also has a web interface, pretty sophisticated web interface actually. So you can interact with it on your mobile device, on a tablet, on your desktop computer, basically wherever. So let's talk about system design goals. Everything in the ecosystem must leverage low-cost, widely available commodity hardware. The system must be inexpensive. So I didn't want to design something that was going to cost a bunch of money. The system should support multiple concurrent time domains. I didn't realize I wanted this until I was halfway through developing it, and then I had to kind of re-engineer everything to get this. and I'm calling them realms. And when we get to the demo portion, you'll see what a realm is. But yeah, multiple time domains. The system should be sufficiently generic such that it isn't limited to model railroad. I figured while I'm doing it, I can think of a bunch of other use cases where synthetic time would be appropriate. So why limit it, basically? The system must support multiple time ratios. So 1:1 through 12:1 was what I was aiming at supporting. Technically, it can support any ratio, but what I have in the UI right now is just you can select from 1:1 to 12:1. The loss of any single component must not affect any other components during an op session or simulation. Redundancy baked in from the beginning. So basically what this means is every client device has its own clock, and instead of like with time code and things like that, if the time code goes away, like everything just stops. I didn't want that, so I've built basically individual monotonic clocks into all of the client software so that they can keep running if the host were to go down. So distributed, highly redundant. Device boot order must not matter. This is kind of self-explanatory. If your whole layout power is on a single switch, for example, a little MCU is going to boot much faster than a Raspberry Pi, and the Raspberry Pi is the host and the MCU is the client. So the client has to be tolerant to the host coming up after it, if that makes sense. The time display should be rock solid on all devices with no jitter or jumpiness, even a 12:1 ratio and even over Wi-Fi. That was very important. The web interface should display current synthetic time and currently connected clients. This is just kind of a nice debugging feature. If you plug in a client, apply power to a client, I want it to pop up on the web interface. You disconnect the client, it disappears from the web interface. You know, pretty self-explanatory. So let's talk about protocol design goals. The protocol must be very lightweight without conflicting with other devices on the same VLAN subnet. Goes without saying, you know, you got Wi-Fi throttles and whatever else running, not to mention other use cases outside of model railroad. So we want to be able to not conflict. The protocol must be Wi-Fi friendly, obviously. Protocol synchronization across devices. So I was aiming at a maximum of 40 millisecond synchronization. Less than 20 milliseconds is better. And this is kind of the neighborhood we're in. For any two clients, they're, 20 milliseconds off from each other is about where I'm at. And this needs to be true even over Wi-Fi, which, by the way, was very much non-trivial to make happen. That was probably the hardest part of this system. The protocol must leverage a simple, easy to implement transport. Anything can be a client. Integration should be relatively easy for, someone who knows a little bit about this kind of stuff. And really, that's just to encourage adoption. Time configuration changes must take effect immediately across all client devices upon apply. So this is kind of just my own eccentricity. I really wanted it to be like you set a new time, you hit apply, all the devices instantly reflect that change. I just think that just tickles my brain in the right way. The protocol must support an arbitrary number of discrete time domains. That gets back to the realms. So I did bake that into the protocol itself. Let's talk about the host design goals, only a couple here. The host application must provide both backend timecode infrastructure, it's not really timecode, but close enough, and a modern, lightweight web interface in a single self-hosting binary, supporting high-level concurrency for large simulations. So I didn't, my use case isn't that large, but I wanted to be able to support, large club layouts or whatever right from the get-go. And of course, the host application must be able to run on inexpensive SBC hardware. So Raspberry Pi, Orange Pi, Mango Pi, all that kind of stuff, and must be cross-compilable. So we did achieve that. Client design goals, and thank you for bearing with me here. We are going to get to the demo soon. So the client applications must be able to run on small microcontroller-based hardware. The core belief here is that inexpensive distributed client infrastructure is more desirable than costly centralized client infrastructure. And then once again, is worth repeating, anything can be a client. Client devices must discover, auto-connect, and auto-synchronize quickly. I was aiming for less than 5 seconds after power was applied, and I have achieved that. Individual clients must continue running even if the host is rebooted or goes down. It is acceptable if synchronization drifts slightly if the host goes down permanently, but it should not impact a simulation or obsession or whatever. And the client algorithm must be repeatable. Protocol integration must be reasonably straightforward. I want people to make their own clients. It would be cool if JRMRI integrated a built-in client for Chronost. Another domain, one of the use cases I'm thinking about, is synchronization and scheduling of residential holiday lighting displays. So like a Falcon Pi player integration would be really cool. That's an area that's kind of lacking in that hobby. So, time-based synchronization is, they kind of support SMPTE, but it's not great. Anyway, moving on. So let's go do a demo. Okay, so here we are in the lab. I must apologize for the dramatic reduction in audio quality. My lav mic bit the dust, and I'm just using the microphone on my phone, so apologies for that. As you can see on your screen here, we have the Chronost Master Clock host application, the web UI, and we're currently running 1-to-1 time. We're using only a single realm, the default realm, and the time is set accurately, or at least pretty accurately. So let's go ahead and turn on the clients here. I have 4 clients, as you can see right here. The reason I've got them kind of staggered like this is they can't be too close together because they are Wi-Fi devices and they will interfere with each other. So anyway, let's turn on the devices. So you'll see once we turn them on, they synchronize very quickly, and we get a client showing up in our selected realm clients here. So we currently have our default realm selected, and it shows us the selected realm clients, Amber Prototype 1, and then all connected clients. And then we'll go ahead and turn on client number 2. Once again, pay attention. Once I apply power, it will synchronize very quickly. 1, 2, 3, go. So it is up and running and synchronized. Pay close attention to the colon blinks on here because they are synchronized seconds with our master clock up here. We'll go ahead and turn on the next 2 clients. Yeah, this one's having some trouble with the Wi-Fi interference, but it does eventually sync. One thing that the protocol does is, like I said, a lot of redundancy baked into the protocol. So if I were to just shut down the host, all of these clocks would continue ticking along. And for a 3 to 6 hour simulation, I would be surprised if they got more than 200 or 300 milliseconds out of sync with each other. You wouldn't notice it, basically. So let's go ahead and do some interesting stuff here. We can bring up our edit window on the default realm. And if I wanted to, I could change the name. Let's talk a little bit about what a realm is. So a realm is a synthetic time domain. Essentially what that means is anything that needs to have its own clock is a realm in this ecosystem. So I can give you an example of a scenario where you might have 2 different realms. Let's say you're a model railroad club and you have an HO scale layout. And we'll go ahead and apply those changes, and we can see that takes effect immediately. And then if we go up here, we can add a realm. And let's say we have an N scale layout. And we want those to operate on independent time. Now, if I create this realm without setting a time, it's just going to borrow the time from the most recently created realm. So they'll be more or less in sync when I first start them. They don't synchronize precisely. And that's an important concept here, is that each of these realms is its own clock. There is no synchronization between them. So even though it grabbed the time, the startup time for the realm, how long it took, it's basically off by, half a second or something like that. But if we want to synchronize them, we can. We can come up here, we can hit pause all, we can come down here and we can edit this, and let's say we want them both to start at 3 o'clock p.m. Apply changes, edit, 3 o'clock p.m. Apply changes. Now you can see that we've got both of our realms are stopped and I can come up here and click Run All, which is going to send a parallel start to each of these, and then they will be operating synchronized. If for some reason you needed to do, I mean, the whole point of a realm is it doesn't need to be synchronized, but if you wanted to, it can do that. But as you can see, we've created two realms here. Whichever realm I have selected is the one that displays the big time up here on the top. So just to illustrate that, let's set this one to 12 o'clock a.m. Apply changes. And now you can see that whichever clock we select is the one that's going to display. Additionally, you can see that our connected clients here for the selected realm disappear when we select the other realm, because we do not have, none of these clients are flashed to the second realm that we just created. You can see here in the user interface, each of these realms has a 5-digit identifier. In the captive portal of the client, that is how you tell it which realm it belongs to. So you essentially reset the client, bring up the captive portal, connect to it with your phone, you tell it which realm it belongs to, and that's how it synchronizes. To get a little bit under the covers here, each realm is its own multicast group, and it pulls from a CIDR range to generate that group. So you can't have an unlimited number of realms, but I think it's 4096 or something like that, which is, I can't imagine a use case where you would need that many. So essentially unlimited. So you can also see that we can stop the time server itself for one. Let's just say we want to pause the HO scale layout and we want to stop the time server on the N scale layout. The main difference there is that when you pause a realm, that realm continues sending out time packets at the broadcast interval you've specified. So you can see we've got this little broadcast interval here. The default is 5 seconds. That's how often the time server is sending out its epoch time, essentially, to the clients. The clients also do a little bit of background synchronization in between. But the point here is that when we stop the time server, we're not sending out those regular interval time packets. When we pause, we are sending out those time packets. There's datagrams, but they are just sending out the same time over and over again, a paused time. In both cases, what you see on your display is no movement. All of the clients just basically display the pause time. The only reason you'd ever want to stop a server, I think, is if you wanted to just eliminate the network traffic. And even so, there's still some like infrastructure traffic that happens, but most of the time traffic goes away. So let's go ahead and click Run there. Of course, this does support fast time. So let's go ahead and set this to an absurd ratio, 12:1, and click Apply Changes. And you will see that all of our clocks start blinking very quickly and start following that 12:1 ratio time. And of course, we can set times lower, or time ratio lower. So maybe we want 4:1, which I think is a more reasonable fast time. And everything syncs. You'll also notice, if you haven't already, if I come in here and I apply a new time, let's say 10:30 p.m., the moment I click Apply, all of these are going to change. So that takes effect immediately. That was a design goal, and I'm really glad I was able to nail that, because it would just drive me batty if they didn't all update at the same time. So now what I'm going to do for the last bit of the demonstration is I'm going to go reflash these two devices here for the second realm so that we can demonstrate the two realms functioning. Give me just a minute and I'll be right back. And we're back. As you can see, the two displays here on the left are following our HO scale layout realm, and the two displays on the right here are displaying our N scale layout realm. So if we come in here and we edit the time for our HO scale layout, we should see only the 2 clocks on the left change. So we'll go ahead and do 10 o'clock AM. Apply changes, and we'll see that change reflected there. And that one is still doing 4 to 1 time. If we come over here to our N scale layout, and we want to start this at 3 o'clock PM. We'll come over here and we'll see that happen. So all of the features are completely independent per realm. So the ratio, the time ratio, the name, the date, and the time, and the broadcast interval, all are able to be specified on a per realm basis. And you can also see here that we have all of our connected clients displayed down here with their associated realm. So, you know, we can change the names if we want to just be more explicit. Realm 1. Realm 2. And you can see that those name changes are reflected immediately everywhere. So yeah, we'll go ahead and pause time here. I think that's all I wanted to show you guys. Hopefully you found this demo enjoyable. And now we can go talk about where I think this fits and where I think it doesn't fit. So let's go do that. So hopefully you enjoyed that demo. Now I'm going to talk a little bit about where I think Chronost fits. So of course, model railroading, that's my use case. I think it fits in escape rooms, haunted attractions, immersive venues, where you want to have some form of synthetic time. I think it could be applicable in museums, exhibits, dioramas, visitor centers, things of that nature. Small venue themed environments that like rely on timed cues. You know, any place you want to synchronize a bunch of people or moving things or whatever. I also think it could be applicable in like LARPs, tabletop, and campaign environments. I think it has some use in training simulations in which like a synchronized synthetic scenario time is required. Themed home automation. So I belong to this really cool Facebook group about people who make home tiki bars. And they do these very extravagant, you know, virtual windows with like big 4K displays behind them. They have like diurnal schedules and things of that nature. And I see them struggling to get all that working. So something like this could really, really kind of help with that, I think. We've talked a little bit about residential holiday lighting, like a FPP integration would be cool. Basically anywhere synchronized synthetic time is required, but less than 20 milliseconds precision is not required. So let's talk about where Chronost doesn't fit. This is not NTP for real-world wall clock discipline. That's just not what this is. It's not precision time protocol for sub-millisecond like industrial or media synchronization. It doesn't replace SMPTE LTC or MTC for, you know, professional show or broadcast environments where there are entrenched standards. And obviously it doesn't apply to things like White Rabbit protocol or interferometry, anything that requires absurdly precise timekeeping. This is not that. Okay. But anyway, I hope you found this video interesting. If this is something that interests you, please comment down below. Let me know how it would interest you, what you'd use it for. And if I get enough feedback, you know, I might upload it to GitHub or something. That's going to be it for this video. Thanks for watching. Thanks for bearing with me. I look forward to hearing from you, and we'll see you on the next video. Bye-bye.